All right, so good morning, folks. I wanted to create this video to go over a topic that there was some discussion board on the Piazza.com website, in which I know I didn't quite adequately cover in class, and unfortunately I don't really have time to probably go over it in our class tomorrow before the exam, so I thought the best way to convey this is through another video. Okay, so this has to do with the fact of combining independent sources, whether it's independent current sources or voltage sources. And so this does apply to one of your homeworks where you had to do source transformations, and you end up with, as you're breaking that down, you might end up with a current source that looked like it was in the middle of your circuit, and some people didn't quite know what to do with that. So I want to show you that there is a valid reason why we can combine these sources, and it all boils down to Kirchhoff's current law and voltage law, okay? So in this case here with the current sources specifically, what we can think about doing is, irrespective of where the current sources lie, we can imagine doing a KCL equation through this bottom node here. So if I just define, let's say, some current I1 coming through that branch, some current I2 going to this branch here, and then let's say this is large I sub A and large I sub B. So if I wanted to write a current equation, a KCL equation, where all currents coming into the node are going to be positive, all the ones leaving out of the node are negative, then I'd have I1 plus I2, this one's going out, so it's going to be minus I sub A, this one's coming in, so that's plus I sub B equals 0. Okay, so this then tells me that if I know what these IA and IB are, because these are independent current sources, they're going to have some value typically in a problem, whether it's 5 amps, 3 amps. I can simply combine those appropriately based on the direction that the current is traveling into a single source. And so in this case, let's just say like this is 5 amps here and this is 2 amps. So I would be able to then eliminate this one entirely, and the total of IA plus IB is going to be 3 amps, right? Because I had 5 going in this direction, but 2 going in that direction, so I had to take the difference, since one was a negative quantity, one was positive. So now I have a net of 3 amps leaving this node. So again, if I rewrote the KCL equation, I'd get the exact same expression in this case, except instead of having 2 terms from my 2 different sources, I've just simplified it to the 1 term for the 1 single source. And so that's the reason why we can combine sources, but current sources only combine in parallel, okay? So you will not run into a case, you can't have 2 current sources in the same branch, because then that would mean you have 2 different current flows, which we know that that's not possible, at least if you're obeying certain laws of physics that we tend to live in. And so therefore you shouldn't have that case. I mean, if I had a current source maybe sitting over here, that would be possible, of course, because this branch is broken out by this other resistor, but I cannot combine, if I have one sitting up here, I cannot combine that with one that's sitting up here, because those are not in parallel. So again, only current sources in parallel can be combined, and we basically just take the net impact, and again, it all boils down to looking at the KCL equations and how we could do that. And then the other thing to point out, again, kind of related back to the homework, is if I do have some current source sitting over here, some people say, well, how can I combine this one when it's sitting over on this side of my circuit and this one's sitting over on this side? But remember that anything in parallel can basically, you could imagine shifting it to however it suits kind of how you see things. So if I wanted to, I could redraw this circuit by putting that current source right over here. Okay, removing it over here, and I've done nothing to change the circuit, okay? Because again, in parallel, the voltage is still the same. The voltage drop across that current source is still equal to the drop across this current source. So I haven't changed anything about the circuit. So again, if that helps you kind of see things better, to redraw things, to put them together before you combine them, of course, that's perfectly acceptable. The net result will still be the same, such that I can combine these two, eliminate one of these entirely, and I'm left over with only one current source, and in this case in parallel with the resistor. And so this is in the homework problem, homework number 7, I believe. this is what you should be getting down to, okay? So I think we needed to solve for the current through a given resistor to the far left side. And so you should be able to simplify that entire circuit down to something that looks like this, okay? Where the current that you're trying to get at was this one, I think. Okay. So that's what you try to get in that problem. Okay, now similarly with voltage sources, the same thing can apply. But in this case, I could do it through a KVL type of expression, right? So let me get rid of this one here. So again, let's just say like this is going to be a voltage drop V sub 1. I got a current source, let's call that VA. Let's call this one VB. This is a drop. Let's go around this way. V2 minus. Okay, so again, I could write a loop equation around this loop here. So I have a voltage drop V1. I have a voltage rise here, so that's plus VA. Coming around, I have a voltage drop across V2. And then again, a voltage rise from VB. Sorry, this should be minus VA, because that's a voltage rise, and a minus VB. Again, all equals 0. So again, now you can see, despite the fact of where these voltage sources are within respect to each other, despite the fact that they have these resistors sitting in between them, they're still in series, okay? And if I just simply write this KVL expression here, you know through basic algebra that it doesn't matter how I rearrange these terms, I can still get to the point where I have this minus VA minus VB that I could combine. If I know what those values are, I could eliminate one of these sources entirely. And so this one would simply be VA plus VB. Again, since these were had the same polarity, they would simply add compared to the differences in polarity on the current sources here. And so I could break that down as such in my expression. But again, that only applied when I had voltage source in series. There was nothing else. Like I didn't have another branch. You know, if I had another branch with some other resistor here and my source here, you know, that would not hold up. Okay, but if I simply had those in the same loop and just directly in series with one another, then I am able to combine those voltage sources similarly to current sources in parallel. So again, this key difference: current sources in parallel you can combine, voltage sources in series you can combine. They do not work the opposite way. All right, hopefully that will clarify some of the questions, and but let me know if you have any other offshoots. There's on our online discussion, and see you in class.